Welcome to this explainer. Today, we're jumping straight into the invisible, microscopic tug of war that actually dictates how organic molecules behave, react, and shape the physical world around us. You know how some chemicals are crazy reactive and others just sit there completely inert? Well, the secret is all about how their electrons are constantly being pushed and pulled. Let's get right into it. Here is what we're looking at today. We'll start with the subatomic tug of war, then hit the inductive effect, move on to the electromeric effect, check out resonance, dive into hyperconjugation, and finally wrap up with why all this electron displacement actually matters. Section 1. The subatomic tug of war, establishing the rules of attraction. So there is a really clear divide here between permanent and temporary effects. Think of permanent displacement like a literal permanent magnet that's constantly pulling. It's caused by atoms or groups that are just permanently built into the molecule's structure. On the flip side, temporary displacement is more like an electromagnet. It is completely switched off until an outside reacting chemical gets close and effectively plugs it in. Section 2, inductive effect, the power of proximity. Okay, so the inductive effect, which we just call the I effect, is a permanent change in the polarization of a covalent bond. And why does this happen? Literally just because of who is standing next to whom in the molecule. It's a permanent shift caused strictly by the sheer presence of adjacent bonds, atoms, or groups. To visualize this, let's compare ethane to ethyl chloride. Ethane's carbon-carbon bond is perfectly balanced, totally nonpolar. But if you attach a highly electronegative chlorine atom to make ethyl chloride, boom, you turn that neutral bond into a polarized tug of war. The chlorine permanently pulls the shared electrons toward itself, creating a slight negative charge on the chlorine and a permanent slight positive charge on the carbon. It kicks off a chain reaction of pulling, although to be fair, this effect fades out pretty fast and is basically insignificant after about 4 bonds. And this perfectly illustrates the hierarchy of power in this subatomic game. You've got your negative I groups. These are the electron withdrawing heavyweights, highly electronegative groups like NO2, cyanide, and halogens that aggressively pull electrons away. Conversely, you have the positive I groups. These are your electron donors, like bulky alkyl groups or alkali metals, which actually push their electron density inward toward the carbon chain. Now, this matters immensely in the real world. Let's trace it out. When a strong electron withdrawing group, like a halogen, attaches near a carboxylic acid group, its negative I effect literally drags electron density away from the acid's hydrogen. Since those electrons are being pulled away, that hydrogen atom is held a lot less tightly, which makes it way easier to just pop off as an H+ ion. This is exactly why trichloroacetic acid, which has 3 greedy chlorines, is a vastly stronger acid than regular acetic acid.
All right, so that covers the permanent shifts. But what happens when the electron shift isn't permanent? What if the molecule just reacts instantly to a sudden outside attack?
Section 3, electromeric effect, flipping the subatomic switch.
Remember that electromagnetic analogy from earlier? That is the electromeric, or E effect. This is a strictly temporary effect operating in unsaturated compounds, so things with double bonds like carbon-carbon or carbon-oxygen. It only activates when an attacking reagent shows up to flip the switch. If there's no attacker, the molecule just sits there perfectly normally. Picture this sequence like a fast-paced sports play. Step 1, an electron-rich nucleophile aggressively rushes a carbonyl compound. Step 2, the pi electrons in that double bond instantly retreat, shifting completely over to the more electronegative oxygen atom. And step 3, because those electrons fled, the carbon is left electron deficient, leaving it wide open to instantly form a brand new chemical bond with the attacker. So a temporary shift actually allows for a permanent new connection. Section 4, resonance, the electron relay. Resonance, or the mesomeric effect, happens when an organic compound can be accurately drawn as multiple different structures that only differ in where their bonding and lone pair electrons sit. But the really fascinating part here is that the actual molecule doesn't look like just one of these rigid structures jumping back and forth. Instead, it is a perfect, seamless hybrid of all of them. Take 1,3-dibutadiene as a prime example of this in action. Based on a standard drawing with alternating single and double bonds, you would expect to see unequal bond lengths between the carbons, but observed reality is totally different. All the carbon-carbon bond lengths are exactly the same. Why? Because resonance completely delocalizes those pi electrons, spreading them across the whole structure to create equal hybrid bond lengths across the entire board. And just like we saw with the inductive effect, substituents in resonant systems act as directors. You can have a positive mesomeric effect, where groups like OH or NH2 release electrons away from themselves and push them into the conjugated system. Or, on the flip side, a negative mesomeric effect, where gritty groups like NO2 withdraw those electrons toward themselves. The crucial takeaway here is that this electron relay provides incredible stability. This is exactly why phenol is so highly acidic. When phenol gives up a hydrogen ion, the resulting phenoxide ion is incredibly stabilized by this positive M resonance effect. It spreads that negative charge around beautifully, completely avoiding the energy-draining charge separation that you see in the original phenol molecule. Because the resulting ion is so incredibly stable, the molecule is perfectly happy to lose that hydrogen. Section 5. Hyperconjugation, the Baker-Nathan effect. So, hyperconjugation is a permanent, stabilizing effect, but its cause is absolutely fascinating. It's the interaction of sigma bond electrons with an adjacent empty or antibonding orbital. This is wild because it involves the usually rock-solid foundational single sigma bonds actually breaking their normal rules to step up and supply electrons for delocalization. Often called the Baker-Nathan effect, this whole phenomenon requires an alpha CH group adjacent to a pi bond. And when it happens, it literally results in canonical forms where, temporarily, there's absolutely no bond at all between a carbon and a hydrogen. This bizarre no-bond resonance perfectly explains why carbocations with multiple alkyl groups attached are vastly more stable than those without. They just have way more of these sigma bonds willing to jump in and share the load. Section 6. Why electron displacement matters. The macroscopic impact of microscopic shifts. So why do all these microscopic pushes and pulls actually matter to us? Well, because these 4 rules are literally the invisible architects of chemistry. Inductive pulls dictate the raw acidic strength of chemicals. Electromeric shifts allow temporary openings for vital reactions to occur. Resonance creates ultimate stability. And hyperconjugation explains why certain complex carbon structures survive while others just instantly collapse. Together, they decide if a chemical is totally inert or dangerously reactive. Which leaves us with this final thought. If manipulating these tiny, unseen subatomic tugs of war controls the very nature of matter, what limits us from engineering entirely new supermolecules simply by rewriting the rules of the game? If we can map and manipulate the inductive pole or the resonance relay, we can design materials that shouldn't even be possible. Thanks for checking out this explainer, and keep questioning the microscopic forces that shape our world.